Welcome to the studio. So, as an apprentice stepping into the professional design world, I need you to do something for me. Leave behind absolutely everything you know about mixing color. Seriously, because digital color isn't powered by messy paint and pigments, it's powered entirely by math and pure light. Today's explainer is going to walk you through my exact professional workflow. We're going to decode the secret language of your design software so you can finally stop guessing and start calculating perfect, harmonious palettes every single time. Here is our roadmap for the session. We are going to start at the atomic level by decoding hex codes, then we'll map those to the digital hue wheel, master lightness, and wrap up by building some perfectly harmonious palettes. Okay, let's dive into this. Section 1, decoding hex codes. The absolute foundation of digital design is the hexacode. But to decode them, we really have to understand why they exist in the first place. You know when you learned about color with paint? You were using subtractive mixing. Pigments absorb light, and if you mix them all together, you get that terrible, muddy brown we all made in art class. But screens use additive mixing. They literally stack red, green, and blue light. In this digital reality, adding more of all your color channels pushes your colors straight toward pure white. So how do we calculate exactly how much light to add? Well, a hex code is written in base 16. That just means after the numbers 0 through 9, we start using letters. So A is 10, B is 11, all the way up to F, which is 15. Finding the decimal value of a single color channel is just a precise mathematical recipe. Let's say we take a hex pair like DA. You take the first digit, D, which equals 13, and you multiply it by 16. Then you just add the second digit, A, which equals 10. So 13 times 16 plus 10 equals 218. It really is that simple. Let's look at the full hex code DA4F70. That DA we just calculated gives us a red channel value of 218. Moving down the line, the 4F gives us a green value of 79, and the 70 gives us a blue value of 112. And honestly, this proves that the hex codes aren't just random gibberish. They are exact light mixing instructions. They're telling your screen to blast a lot of red light, a little bit of green, and a medium amount of blue to create this specific punchy pinkish red color. Let's move to section 2 and see how this builds into the digital hue wheel. Now that we have our primary channels, red, green, and blue, we need to map them out so we can actually design with them. The traditional 120-degree structure you probably already know, that still holds perfectly. The only difference is our primary building blocks. Instead of red, yellow, and blue paint, we have red at exactly 0 degrees, green at 120 degrees, and blue at 240 degrees. Right halfway between them sit our secondaries, yellow, cyan, and magenta. It's the exact same geometry you're used to, it's just mapped to the physics of light instead of paint. And because this wheel operates on degrees from 0 to 360, finding perfect color harmonies becomes a totally bulletproof mathematical workflow. To find a triadic harmony, you don't need to guess by eyeballing paint names anymore. You simply pick your base hue in degrees, add 120 degrees to find your second color, and add 120 degrees again to find your third. And if you go past 360, you just wrap right back around to 0. Why does this matter? Because it gives us perfect mathematical harmony, zero guesswork. All right, on to section 3, mastering the lightness scale. Here's the thing, hue alone is really just a direction. To actually land on a specific color, we have to master our third dimension, which is lightness. This runs on a straight 0 to 100% scale. 0 is pure black, 100 is pure white, and 50% is our dead center pivot point. Now, what's really interesting about this is how specific colors plot out. Take cerulean, the Pantone color of the year for 2000. It sits perfectly at the 72% mark. Because it's above that 50% threshold, it naturally sits on the light half of the scale, which perfectly matches how our human eyes perceive it as a soft, pale blue. Okay, as my apprentice, I want you to pause right here and do a quick practice task. Think about a pure, fully saturated blue, which is hex code 0000FF, and then think about a pure, fully saturated yellow, which is FFFF00. I want you to calculate the lightness for these two extreme colors based on what we just learned about the 0 to 100 scale. Any guesses? Well, you might actually be pretty surprised by the result. Mathematically, in the digital color model, pure yellow and pure blue both equal exactly 50% lightness. They sit right smack on that pivot point. Now, our human eyes naturally perceive blue as being much, much darker than yellow, but the mathematical model treats their lightness as exactly the same. It's a really vital nuance to understand, especially when you're designing for readability and contrast in your digital systems. Finally, section 4, building harmonious palettes. Let's bring all these pieces together. This is where the magic happens. The core of generating flawless secondary palettes is the 180-degree reflection rule. First, we establish our hue by moving exactly 180 degrees straight across the digital hue wheel. That gives us our exact complement. Then we apply our lightness rule. To find the lightness for this new secondary color, you simply take 100 and subtract your principal color's lightness. That's it. This creates a perfectly balanced reflection right across that 50% midpoint. And this brilliantly illustrates the rule in action with our cerulean palette. Our principal cerulean started at a lightness of 72, right? By applying our rule, 100 minus 72, our 180-degree reflected secondary drops down to a rich, dark 28% lightness. From there, we also add secondary companions by shifting the hue 40 degrees in either direction. The result? A palette that is balanced, highly contrasting, and mathematically sound. But hold on. What happens if we want to shift lightness in the same direction instead of reflecting it? Well, we need a safety clamp. Think about it. If you have an extremely light principal color, like Cloud Dancer, which sits at 93% lightness, shifting it up another 15 points totally breaks the system, pushing you completely past 100% pure white. Our mathematical constraint acts as a failsafe, basically ensuring these secondaries are clamped securely between 5% and 90%, so your design never breaks. And to prove to you that this isn't just theory, we can look at the real-world data. We ran 29 distinct Pantone colors of the year, spanning 27 years, through our exact mathematical rules. You can see the 180-degree reflection and the 40-degree secondaries applied flawlessly to every single color. You can even spot where a safety clamp activated for extreme colors like Sand Dollar and Cloud Dancer. This mathematical workflow effortlessly scales across decades of published color data. It just works. So you've officially seen behind the curtain. You've decoded the exact math of light, you understand the digital hue wheel, and you've mastered the lightness formulas that truly drive digital design. The days of just dragging a color picker around and hoping it looks right, those are completely over. So my final question to you is this. Now that you have this professional workflow, what exact harmonious palettes will you calculate for your next masterpiece?